Hi everyone, I'm Huw Day. I'm one of the data scientists at the Gene Golding Institute, and yeah, as Pal said, I'm going to be talking today about an introduction to the theory of neural networks. So I'm just going to quickly share my screen, and this should be visible to people now. Thank you. We've developed a training course which is an introduction to coding neural networks in PyTorch, which is a 3-hour long course, which includes both theory and practical. And so Pal's going to share some of the links to that into the chat. Today, we're not going to be doing any coding, and I'm just going to be going through some of the theory aspects and using some visualization tools that are available online to help give a better intuition as to how some of these tools work. So if at any point you have any questions, feel free to post in the chat, and Pal will be able to answer all of them, I expect, but might defer some to me as well. But yeah, so without further ado, we're gonna crack on. So just a general idea. So obviously this is talking. This page is the landing page for people taking a coding class. You're not doing that, so don't worry if you're not a familiar Python programmer or anything like that. But just so that you understand what we're going to be covering today in terms of theory, we're going to understand the basic theory of a feed-forward multi-layer perceptron. We're going to understand how to feed forward data and evaluate loss for a neural network, and then have a basic intuition for what gradient descent and backpropagation are and how they're used to train a neural network, right? Okay, so back in the 1950s, there was an idea conceptualized thinking about how can we make some kind of decision-making machine that's sort of inspired by neurons in the brain. In a computational capacity, we can consider neurons to be things that hold numbers. And then we can think of connecting these neurons together in such a way that we can start making decisions based on these numbers. So a basic example of a perceptron is drawn here. I'll just zoom in, make sure that's visible. And so the idea being that you have say 2 features about your input data, and you have a label about your input data as well. So this could be like height and weight, and you want to guess, say, the value of like shoe size, or maybe you want to classify, does this person have a shoe size bigger than, I don't know, size 6, something like that. And so the idea is that we have some parameters associated with our perceptron that we can tweak that affect how we transform our values from our input layer into our output layer. And so if you just randomly initialize these, on average, you'll be wrong. And so the idea is that given some data which has some labels, we want to change the values of our weights, these W's, and our biases, B, in such a way that we are able to correctly predict the labels that we have in our data. So the way that we end up doing this is initially with a perceptron. This is kind of linear transformation. So what we do is we take in our x1 and our x2, and we do something like w1 times x1 plus w2 times x2, and then we add this bias b, and then we say, okay, if I want to classify if something has a label of 0 or 1, which could be shoe size lower than 6 or bigger than 6, then I just basically go, okay, I load this thing in and see if the value is less than 0, then I say that my label is 0, and if it's bigger than 0, I say my predicted label is 1. So mathematically, this seems like sensible, but not particularly intuitive to visualize. And so one way that I like to think about this is with a sort of more geometric intuition. When we generate these sort of outputs, in some senses, what we're doing is we're getting a perceptron to say, this is the probability I think that your individual data points fall in a particular class, being class 0 or class 1. But when we think about it geometrically, we can think about drawing a line, or sometimes called a decision boundary, to separate our data, right? So apologies, I'll have to scroll through quite a lot of the code here, but to take a concrete example, let's consider a really simple example of a data set of 4 points. And so my 4 points are going to have features 0, 0, 1, 0, 0, 1, and 1, 1. And my labels are going to be based on something called an AND gate. So if you ever studied computer science, and you know about logic gates, AND takes in 0 and 0 and returns 0, and 1 and 0 and 0 and 1 and returns 0, and it's 1 when both inputs are 1. So if x1 and x2 are both 1, then it returns 1, and otherwise it returns 0. And so what we can do is we can look at here this plot where I have my zeros from my logic gate being these blue circles and my 1 from my logic gate being this red triangle. And then we can think about what are sensible values for my weights and my biases, so that I can draw a decision boundary that separates the 2 points. And so now if you're trying to interpret this decision boundary, you can go, okay, everything on the left-hand side of my decision boundary is class 0, and everything on the right-hand side is class 1, right? Kind of makes sense. And so we're not dealing with yet working out how to automatically find the right value, but we can kind of think about like, okay, if we know there is a right value, then all we have to do is think about a sensible way to find it. But knowing there's a right value is an important first step. So you can see that if we plot lots of different values for B, our bias, then we end up with lines that have the same slope, but have different intercept on the y-axis. So again, because our decision boundary from our simple perceptron is just is essentially just a linear equation, we're drawing a line that looks like y equals mx plus c, which you might have seen like in a high school maths class. Where m is just the slope of the line and c is just the intercept of the line with the y, or in this case, the x2 axis. So in this case, concretely, the bias b tells us something about where we intercept on that axis. And so you can see that actually there's a range of values for b that are valid for given if I fix my 2 weights w1 and w2, then all of these are valid decision boundaries to separate this data. In practice, for these sorts of classification tasks, you'd have a lot more than 4 data points, but just for illustrations, it's quite nice to look at. You can also think about what happens if we vary the weights. So in this case, I'm going to fix W2 and the bias B, but I'm going to vary W1 across a range of different values. Because the bias is fixed, our intercept stays the same, but for lots of different values of W1, I'm still able to successfully classify all my points of interest, right? So this is somewhat reassuring to know that for lots of cases, your exact solutions is not like a precise number, but it's a sort of a collection of weights and biases for a given perceptron in this case, right? However, what we'll see is that it is really easy to construct a case where the simple perceptron is not able to classify data. So take the same sort of x1, x2 features. We're now going to use the exclusive OR logic gate to generate our y labels, so in this, or sometimes called XOR. So this is this takes the value of 1 if one of x1 and x2 are 1, so this row here and this one here, but it takes the value of 0 otherwise. So both zeros give us a 0 and both 1s give us a 0 as well. So now if we look at what we're dealing with now, so we have these 2 blue circles are our 0 class and these 2 red triangles are our 1 class, and try as you might, you will struggle. In fact, it's impossible to draw a straight line that separates these 2 points, these 2 classes of points. So we need to start thinking about what can we do to make our perceptron more complicated so that it can deal with more complicated tasks. We want it to be able to draw an arbitrarily complicated decision boundary. Okay. I should note I'm going to be going through these here, so you should just focus on my screen. But I think afterwards, yeah, I can see Pal's already shared the link in the chat, so you're able to download this code and change some of the values and run stuff if you'd like as well. So we need to make our perceptron more complicated. So what are we going to do? So some of the things that people have done is they first considered this idea of non-linearity. So we saw that we were drawing straight lines of best fit, and we want to do something to make these lines not straight anymore. And so a kind of fairly obvious solution is to just take your linear function and then just add something to it, like compose it with another function that makes it non-linear. Another thing to think about is we want to make what we might call the architecture of our neural network more complicated. So instead of just having a perceptron where you have an input layer of some neurons and then an output layer, we want to have some stuff in the middle to sort of jumble things up or sort of transform our space and our points in some sense. So There's some code here where you can where we have a more complicated structure for a neural network, where we have what's called a hidden layer, where because we have a fully connected neural network, every neuron is connected to every neuron in one layer is connected to every neuron in the next layer. So you can see that there's an arrow going from this X1 neuron to both neurons in the hidden layer, and then these guys feed forward into our output layer like this. If we don't have a non-linear activation function, then what we are essentially doing is just taking a linear function of a linear function. And you could have arbitrarily many hidden layers in your neural network, but what you will just keep doing is you'll just end up with a linear function. And we know from kind of high school geometry that if you do a linear function of another linear function, you just get a linear function spat out at the end. So there's some code here that lets you put in lots of different values for weights and biases, and you can put in all the different values you like, but you're always going to end up drawing a straight line, right? And so we can see here that if we compose two linear functions, then we just get something else that looks like a linear function, right? So as I mentioned, the way that we address this is that we want to introduce these non-linear activation functions to account for this. Now, there are lots of different kinds of activation functions, so I'm going to mention 3 of them today. You might want to read into a bit more depending on your domain application, which one you might end up using. So the first one that people ever used was this sigmoid function. If you've ever studied logistic regression in a statistics or machine learning class, then this might be familiar to you. It's sometimes called the logistic function, but it's essentially a function that squishes any value between minus infinity and plus infinity on the real line into an output between 0 and 1. So it has this effect of making it look like a probability, so that can be quite nice. It just takes this form. It's 1 over 1 plus e to the minus x for any input of x. The second and arguably the most common activation function is called rectified linear unit, or everyone calls it ReLU for short. So what it does is it returns 0 if the input is negative, and it returns the input value if the input's positive. So it just is actually just the maximum of 0 and x for a given input x, right? So it looks kind of like a weird sort of kink like this, but you'll see it in a sec. And then the last one is this hyperbolic tangent, sometimes pronounced tanch, which you may have seen if you've ever studied hyperbolic trig functions, but if you haven't, don't worry about it. But this has the effect of squishing all your inputs into an output range between -1 and +1. And this is commonly used in certain types of recurrent neural networks, which have applications in like time series forecasting, where you want to say you have a stock price over time and you want to try and guess what it's going to be like tomorrow, but also in stuff like natural language processing as well. And so there's some nice little code here that plots these 3 values for you, like so. So I've just plotted between -10 and +10, but you could plot it for a bigger range you like, and you'll see that it will always squish between the values that I've mentioned already. So now what we can see is that there's some code here that now feeds forward data into a neural network of the architecture I showed already, with 2 input nodes, 2 neurons in a hidden layer, and then an output layer, and is able to draw a decision boundary because it's using a nonlinear activation function. So in this case, a good activation function, is the hyperbolic tangent, and so it actually ends up drawing a line that kind of loops like this, and so that means that you're able to capture one of the classes in the middle and exclude the other classes on either side. And so that's able to solve your classification task problem for you with a neural network that is this complicated. So in the grand scheme of things, not very, right? And so far we've been talking about problems in 2D, but as I'm sure if you've worked with data before, often your classification tasks or your machine learning tasks have more than 2 features of your data. And so the analogy of drawing like a decision boundary around points extends quite naturally into higher dimensions. If you can visualize 3 dimensions, you basically think of yourself as like drawing a sort of, or pulling a sheet, like a bed sheet, around your points so that it separates different classes of points from each other. You can also look at situations where you're classifying more than 2 classes. In that case, you're essentially doing a sheet that is somehow able to go, okay, well, to the left of of these points is one thing, to the right of these points is another thing, something like that. But I try and keep that general intuition in my head. Obviously, when you start getting to higher and higher dimensions, visualizing that becomes intractably hard. But if you just kind of go, okay, well, 10 dimensions is kind of like 3 dimensions, but 3 is actually 10, you can just sort of think about like, okay, well, I'm still drawing some sort of bed sheet around my points to wrap them up and separate them from the other classes. Okay, but that's how I try and visualize these things sort of geometrically. Cool. So the last thing to think about, which is a little bit more pragmatic, which should be a familiar concept to you if you've studied any machine learning or statistics before, is thinking about how to evaluate these multi-layer perceptrons, right? If we think about it, if we have data with labels, then predicting it is in some sense useless, because if you already know the answer, why would you want to just repredict them? What you're actually trying to do is learn, and as in teach your neural network to be able to classify points it hasn't seen before. And so if you only show it data that it's seen before, then if you only get it to try and classify points it's seen before, then it's kind of cheating. It's kind of showing it the answer to the test. And so you want it to be able to answer other questions from the same subject that it hasn't seen on the test before. In practice, if you've ever done any work in data governance, it's a pain in the neck to kind of go and get a load of data, train a model, and then go and get some more data. So what you do is you get all of your data, and then before you train anything, you separate it into a test set and a training set. And so what that means is that you will train your neural network, so which we'll talk about more in the second part of the theory. You'll train it on one set of data, and then on a completely separate set of data from the same data set, you will then evaluate how good of a job it does. And so the idea is that you train it on one side and then update it, and you look at how it did with the tests, and then you use that information to update it the other way. How do you think about updating it the other way? Well, before we think of the how, we almost want to like set the problem up in a particular way. So if you get a chance later to play around with any of the Python functions that we've shown here, you might see that just randomly guessing values is really hard. You could, in theory, just get Python to just randomly initialize some weights and some biases, have a guess, and see how it does, and it on average will be wrong, like most of the time. And so what we want to do is we want to measure how wrong we are, and then tell our code that, and get our neural network to use that information to improve. There's a whole kind of field of different kinds of loss and or cost functions, but these are just methods of evaluating how good of a job you've done on a supervised task, like classification or indeed regression, right? So in this course, we talk about mean square error a lot, which should be kind of familiar to you. So if you had a classification task, say your input was images of dogs and cats, and if you did something where you said, okay, well, let's say my error for each individual instance is the difference between the guess and the answer. Let's say that my neural network had 2 data points that it fed through for its test set, and it got them both wrong. So I got a 0. 0 was the right answer, and 0 was the observation, and I have to subtract 1, which was my prediction. But then in the other case, 1 was my observation, and I had to subtract 0 because I got it wrong the other way. If you add up these errors, then you'll get 0. They'll cancel out. And so that if you want each of your individual error observations to be positive, so that if there's lots of things wrong, they accumulate, then a simple way to make sure that they're positive is to square them, right? The square of any real number, positive or negative, is always going to be positive, or at least non-negative. And so that's what we do. In practice, what we also want to do is that we don't want our loss to be affected necessarily or directly by the number of data points, say, in our test set. And so what we do is we just do what's called the mean squared error, where you just say if you have n data points, and for each one you have an observation, which is your label y, which we saw previously. And then we have a prediction, which is just what our neural network predicts the label is. Then we just take essentially this weighted sum, where you divide by the number of observations, and then you just do observation 1 minus prediction 1 squared plus observation 2 minus prediction 2 squared, and so on and so forth. Cool. And so yes, as I said, what we're interested in is out of sample predictive power. So we want to not just be able to predict stuff we've already seen. We aspire to have our model to be able to predict things that it hasn't seen before. And so yeah, there's more there, and this is quite an important. Basically, anytime you're doing any kind of machine learning, you should be doing a test train split of your data for supervised tasks, definitely. Okay. So now what I'm going to do is now what we've done is that we've seen we can get some data with features X and labels Y, and then we can define some structure of our neural network, say, of our multi-layer perceptron, and then we can initialize some weights and some biases that affect the values of things that get fed through our neural network. Once we've done that, we can make some predictions, and then we can measure how good of a job we've done making those predictions. So now what we want to think about is how can we use our information about our, like, how good of a job we've done to make our neural network better at making predictions. So if you think about it, the predictions are a function of our input data and our weights and our biases. And our error is a function of our predictions and our observation. What that means is indirectly changing our weights and our biases will affect the error. And so what we want to do for something called gradient descent is think about how we can affect that. So I'm not going to really scroll down here because the demos I've made are kind of static and janky, but I'm going to talk a little bit and I'm going to show some visualizations that might be helpful. So the way that I consider this problem is that you can end up with what looks like, yeah, so maybe I'll just quickly show. So here is an example where instead of having a proper neural network, I just have a linear model, and then I have a function I'm trying to approximate. In this case, it's just a sine function. And so what you can see is that if I pick some values for the slope and the intercept of my linear model, then I can calculate the mean squared error. But what you can also do is think about the plot that looks like, how does, say, the value of one of my weights vary? How does that affect my mean squared error? And you start to see this kind of slope here. Now this slope is quite a kind of arbitrary one because I've picked a really simple model. But in higher dimensions, because we have more than just one weight, we start thinking about something that you might refer to as a loss landscape. So if you imagine you're hiking in a misty mountain and the height of the mountain is actually your error. So you're trying to go downhill, right? And then all the different directions you can go, obviously, like we live in 3D space, so the directions you can kind of go is just sort of like north or south and east or west. But if you just imagine that example for now in 2 dimensions, then you could think about the problem of trying to go downhill. But the problem is that if you wanted to know the entire sort of what the whole mountain range looks like, you'd have to calculate the error at every different value for weights and biases. So if you imagine instead that it's really misty and you can't actually see what the rest of the landscape looks like, but you can feel the ground underneath you, and you want to go downhill because you want your error to go smaller. So what you're actually going to do is you're going to feel the ground underneath you and go, okay, that way, say northeast is downhill. I'm going to take a step in that direction. And then you say take a step, maybe take a couple of steps, you stop, and then you go, okay, now it feels like going north is going to be more downhill. So I'm going to go that way. And maybe you're going to take a step proportional to how steep it is, right? So take a larger step. And then what you do is you keep doing this and you keep going downhill. And then say eventually you get to like a dip at the bottom where any direction you go is uphill. That means that maybe you should stop because you've gotten to a place that's down, that's sort of at the bottom of something. In practice, you could get to like a valley that's sort of local, but there's actually a deeper valley next to it. And so there are some clever algorithms people use to try and mitigate this problem. But in general, that would be a wise strategy to take if you were hiking and you couldn't see. but you could feel where the ground was. You might conservatively take a step and then feel which way is downhill and then take another step, right? So I'm going to try and screen share this. It looks quite wacky, so I hope it's kind of visible for everyone. But what we can do is we can imagine a situation where, so in this case, I have, let's think of the best way to view this. So at the top here, I have a blue function, which is actually just x squared, and I'm trying to approximate it with a neural network, which is just which is a very simple perceptron, but it has a nonlinear ReLU activation function to it. And what I can do is I can say randomly initialize some weights and some biases, and so you see that the green line moves. And then down here, you can also see that randomly initializes a point. Now I'm going to initialize it again so it's somewhere like higher up. Cool. And then what you can do is you can say, okay, and so this is your hiker on the Misty Mountain, and the arrow that you can see is the direction they can feel that the slope goes. And so I can take a step in that direction, and I can take some more steps. And I can keep going downhill. Maybe if I randomize it again, so I'm trying to see where it is. This is what happens when you do live demos with someone else's tool. I should hopefully Pow can share the link to this. This is not a tool I've made, but it's a really cool tool for exploring this kind of thing. But so I can take a step and I can start seeing that gradually you see that at the top of the screen this function starts moving closer and closer to it. And then you can also see that this little hiker now is moving downhill further and further and further. So if you randomly initialize it again, to actually train, if you just click this button and start it somewhere where it's wrong, maybe I'll just change the function so it's a bit more complicated. And I'm just going to change the activation function as well, so we just get something a bit more wacky looking. There we go. Cool. So now if I step once, then I start going along, and now if I click the train button, then over time I will gradually start moving along. Now at the moment it's taking a really small step size, but you can see that it's slowly moving its parameters along, right? And you can even say, okay, actually I want you to take a bigger step. And now it starts speeding up. It starts going downhill, and you start seeing this plot here starts getting, now obviously this function is never going to do a good job of perfectly imitating this, but it's a nice start, right? And so it's gradually moving to this sort of bottom valley here. Okay, so hopefully that gives you an intuition of like the process by which you could think about moving down in your loss surface to try and improve your guesses, right? So this is a process that's called gradient descent. So if you've studied calculus before, then you might understand that you can think about a slope of a function as its gradient. So in one dimension, you might have heard of like a derivative. There's kind of dy by dx, and that's just describing what does the slope of my function look like at the position that I'm at, right? And so, for example, the slope of a linear function is just, so if y equals mx plus c, then your gradient is just m, the slope, right? But with more complicated functions, the slope is itself a function of your position, right? So what you're trying to do is trying to get your slope to be small so that you're getting to somewhere that's flat and hopefully low. How do you do that in practice, though? So backpropagation is best explained with a bit more advanced calculus, including something called the chain rule, where you can actually start thinking about like how does the derivative of the error function depend on the derivatives of the different weights and biases. I'm not going to go into that today because I wanted to assume a sort of slightly lower of mathematical insight. Although at the end I'm going to link some, hopefully Pow is going to link some resources to some things about calculus and linear algebra. And also the videos, which I have cited here, where I've gotten some of these images. So the idea of backpropagation is that we want to have an algorithmic way of updating our weights and our biases of our multi-layer perceptron using gradient descent. So the first thing that we do is that we do a forward pass where we pass all of our training data to compute some predictions, and then we evaluate how good of a job we've done with our loss function. Once we've done that, we take this gradient descent approach and go, okay, I want to move, and obviously if you have more than two weights and biases, you're not going to move northeast. You're going to have some idea based on your gradient vector. Your gradient vector is going to point uphill in your lost landscape. You just want to go the other way, and you can also tune how far do you want to jump the other way. Do you want to take one step or do you want to take lots of steps? What you do from there is you start at the end, so your output layer, and you look at how you use the gradients to understand how much does each of the neurons in the final hidden layer affect this guy. And then you know, okay, actually I need this value to increase by some amount. And so because using calculus, you have some understanding of how each of these neurons and their weights and biases affects this value. You know that, okay, if I increase this one a lot, then it will change this. It will also increase this value. If I decrease this one a little bit, it will decrease this value a lot, say. And so you do that one layer back to try and get a better prediction on your output layer. And yes, Pal's just shared some of those YouTube courses in the comments. Thank you. And the idea of this picture is to express how complicated this process is that once you've done it for your hidden layer, you now want to go, well, I have an idea of what a more optimal value for each of my neurons in my hidden layer look like. So now what I'm going to do is I'm going to look for each one of those and go back and go, okay, well, how can I change everything in the weights and the biases in the layer before to try and affect the neurons in my final my final hidden layer. And so you just keep propagating this process back and forth using gradient descent. So you update the penultimate layer, the final hidden layer first, to affect your output values, to make them closer to being the right answer and to make your error function smaller. And then you keep going back until you get to the first hidden layer. And so once you've done this for all your data, that's one pass. And then typically what you do is you just do this multiple times. And so you're moving throughout your lost landscape and trying to move further and further downhill until you get an error that looks relatively small, right? And so once you've done this for all the training data, you then run it through your test data, and then that will give you an idea of your test loss. So that will be like, okay, how good of a job is my neural network doing at guessing stuff it's not seen before, right? And then we don't update our weights and our biases on this data. We only update it on our training data because we've made sure those two are completely separate, right? So, and so this was, this was kind of being shown here. So if I randomize my model again and I turn off train for a second, then what we're essentially doing is we're just going downhill until we find somewhere that's relatively, and this is kind of a relatively flat section here, right? So hopefully that process kind of makes sense. So the last thing we're going to do is I'm going to show you this fun little tool. It's called the TensorFlow Playground, which hopefully Powell will link. Just a warning, if you have anything important to do in the next couple of months, this will be really fun and a great way to procrastinate doing that. But what we can start thinking about is how can we visualize this decision boundary process? So you recall I mean, I know we only showed like 1 or 2 points, but we could think about a perceptron, which has 2 input layers and an output layer, and no hidden layers, and it has linear activation functions here, and say, well, how would training this look? And so I can reset it, and then in this case, it's going to go really, really well. If I pause for a sec and just make one of these weights arbitrarily large, too large, Huw, too large. This is the wrong weight to be changing, excuse me. So if I change this weight, great. Then I can start making sure that this fits better. You can also make it show you like test data so that you're seeing that there's sort of 2 separate bits of data and it's only updating based on the training data. But you see that it's running through all these epochs and your test loss has gone down to 0. But now if we have something, I'm sorry, I'm going to remove the test data. Now we have something that looks more like our exclusive OR problem, where we have 2 classes, some stuff on the off diagonal and some stuff on the main diagonal. If I just try and use a linear decision boundary, a linear perceptron here to separate them, then it gets stuck because it can't improve any further. And so what we saw is that we did something where we added, say, a hidden layer with two neurons, and I think we used the hyperbolic tangent. And I think if we hit play here, then we can start to see it starts trying to separate them. And it does a decent job. But you might go, oh, okay, well, maybe it's not complicated. And so what you can start looking at doing, and this is unfortunately the science of training a neural network is a bit of an art because you just have to sort of think about what's the right things to try. And so maybe what you might do is maybe make, okay, let's add another neuron to my hidden layer and see how that does. And so actually you're saying, oh, well, maybe it's still having trouble kind of making sure that these are completely separated. So instead, what I might do is I might add another hidden layer with another two neurons and see how that does. Let's try. Sorry. There we go. So in this case, it turned out one hidden layer was good, and if I just use 4 neurons in my hidden layer, then I'm able to pretty accurately draw a decision boundary that separates my points. And that's how that goes there. But then what we start seeing is you can get more and more and more complicated situations. So for example, what if you had data that looked like this? And how would you think about going to separate this? So what we could do is we could just hit play and try this. And in this case, it turns out that the hyperbolic tangent does a good job of drawing stuff around it. But maybe we're more like, okay, well, how will ReLU do? So we hit play. And in this case, you can see that this decision boundary has these kind of sharper edges because our ReLU has like a linear bit and then a sharp turn and then another linear bit. And so it ends up making those decision boundaries like that. And then you get to really complicated things where you've got this sort of interlocked spiral and you say, okay, well, does that do any good? And you can see actually this architecture of a neural network is not complicated enough. And so as a fun exercise, I'm just going to like hit play and hope for the best, but I don't think it's going to work with such a simple setup. So yeah, that's the general theory of how a neural network works. So I think when I was first learning about AI, it seemed quite like a mystical thing, but all you're doing is, in supervised tasks at least, is you're just trying to predict a thing. So in this case, you're just trying to predict a label to a number. But what you might also think to do is, for example, LLMs work by they turn text into numbers, and then they go, okay, given a bunch of words, can I predict the next one based on data that I've seen before? So yeah, so that was all that I was going to talk about today. So thank you very much for listening. But I'm very happy to answer any questions if anyone has anything they wanted to ask.